In this lecture, we talk about a dipole. So what is a dipole? So dipole is a pair of equal and opposite point charges, say q and minus q, and they are separated by a small distance. So in the figure which we will draw, the distance between q and minus q would be 2a. So say you have charge q here, charge minus q here. So first we mark the center of the dipole. So let us mark this in green. So q is at a distance a from the center, and minus q is also at a distance a from the center of the dipole. So we want to compute the electric field associated with this dipole. So say you pick a point P in the space. So this point P, so if you put the center of the dipole at 0, 0, then this point P is a distance r from the origin. So the coordinates of P are r cos theta and r sin theta. So similarly, you can put coordinates of minus q as a comma 0 and coordinates of q as minus a 0. So first is r1 vector. So r1 vector is going from A to point P. So this is AP vector. So we are putting the test charge at point P. So therefore the direction vector is pointing towards the test charge. Now AP vector is nothing but OP vector minus OA vector. So we will write OP vector as r cos theta comma r sin theta, or you can say r cos theta I vector plus r sin theta j vector. You subtract minus a 0. So you get r cos theta plus a comma r sin theta. Now it is important to note that you could just have taken the coordinates of point P and point A and done a standard subtraction. So similarly, you have r2 vector, which is PP vector. So first take P vector, angular bracket r cos theta comma r sin theta, and then you take coordinates of OB vector, which is a comma 0. So you get r cos theta minus a comma r sin theta. So these are the two vectors associated with the position of the point P. So we are placing test charge at some point P. So first, electric field associated with the point A or charge Q. So you just write the definition. You have EA is equal to K times Q over R1 square times R1 hat. So where R1 is the length of the vector R1. So similarly, EB is K times minus Q over R2 square times R2 hat. Now where R2 hat is the unit vector associated with R2 vector, and R2 is the length of the R2 vector. So we take the sum of these two fields and you get the field of the dipole. Now case 1, so theta is 0. That means point P lies on the x-axis. So R1 vector would be, just put theta equals to 0. You get r plus a, and sin theta will be 0. So second coordinate will be 0. So length would be square root of r plus a square plus 0 square. That will just be r plus a. So the unit vector would be r1 vector divided by length of r1. So r1 vector we just saw was r plus a comma 0, and length of r1 is r plus a. So this gives you angular bracket 1 comma 0. This is same as I vector. So EA vector is equal to K times Q over this R1 square is R plus A square times 1 comma 0. So that means we only have the first coordinate is the x coordinate, so only the horizontal direction. So only the x axis we have. So for R2 vector you have R minus A comma 0, that is you put theta equals to 0 for R2 vector. So similarly length of R2 vector would be R minus A, and the unit vector associated with it would also be 1 comma 0. Same computation as before. Instead of R plus A we are writing R minus A. So EB vector would be equal to, that is electric field at point B is K times minus Q or minus KQ divided by R minus A square times 1 0 in angular bracket. So there is nothing in the vertical direction, everything is in the horizontal direction. That's why in the angular bracket we only have 1 comma 0. So you add it up, forget about the vertical direction, you just take the horizontal direction. So you have KQ comes common outside, you have 1 over R plus A square minus 1 over R minus A square times I vector, and you can write plus 0j vector, but we will just ignore it. So this is the total dipole if the point is on the x-axis. So what if theta is equal to pi by 2? So for case 2 you put theta equals to pi by 2. Now cos theta would vanish here. So R1 vector immediately comes out to be A comma R. And if you take its length, it will be square root of A square plus R square. Similarly R2 vector would be minus A comma R, but its length would also be square root of minus A square plus R square. So EA vector is K times Q over R1 square. Now R1 square now would be R square plus A square, that is length of R1 vector square. Put R1 vector here, and then you have EB vector, which will be minus KQ over R2 square, but that is again R square plus A square. Yeah, square root of minus A square plus R square is the length, and you take it square, and then times minus AR. So in this case we have both vertical and horizontal component. So let us see if something cancels out. So you add them, obviously you take KQ over A square plus R square as common outside. So let us take this out. KQ over A square plus R square is out. So now the first coordinate is A plus A, minus minus cancels out in EB, but the horizontal component becomes R minus R, which is 0. So we get two A KQ over R square plus A square I vector, that is only the horizontal direction. This is the electric field due to dipole if theta is pi by 2. So again the length of R1 vector is nothing but square root of R square plus A square.